Hi everybody, I'm Tom Svilans, and I'm super happy to present our paper called Model to Press Digital Data Flow for the Design, Rationalization, and Manufacture of Freeform Glulam Beams. So maybe a little bit less abstract than some of the previous presentations. Before getting into the paper, I'd like to quickly introduce the partners. ZAZA Timber is a family-owned company in Latvia that works across the entire timber construction chain. From structural engineering and DFMA through Glulam manufacturing to on-site assembly. And that means that this integration, the research is driven by real production challenges rather than purely academic questions in the laboratory. ZAZA's strength is that they combine engineering, manufacturing, and construction under one roof. And this allows digital methods to be developed and tested directly in an industrial production environment. So they also have an established track record of design build of mass timber projects across the Baltics and the Nordic countries. That also feeds into this. So as projects have become increasingly complex, the company established an R&D department to convert one-off project challenges into reusable methods. And the goal of this department is to bridge engineering, factory production, and research so that new workflows can eventually become standard practice within the company. Then we have the MECA, or the Forest and Wood Products Research and Development Institute, also in Latvia, which contributes research and testing expertise. And they support the project through mechanical testing, prototype validation, and the development of the process technology itself, ensuring that the digital workflow corresponds to the physical behavior that we see in the actual material that we develop. In this project, MECA is responsible for several complementary activities, developing the 3D press concept alongside the digital workflow, carrying out the mechanical testing of the different Glulam specimens, and connecting the digital models with the physical manufacturing process. So the project context. Today, the formal potential of freeform Glulam has been demonstrated by pioneering projects, such as the one on the side, among many others. The computational modeling tools and methods to design such projects have likewise matured considerably. And this has increased the demand for complex solutions as such methods become more widespread and more readily available and accessible. So the challenge today is no longer how to model these geometries, but how manufacturers can reliably and systematically estimate, rationalize, and fabricate them. So of course, while the ideal scenario is that the producer works closely with the design team from the very beginning of the project, as we all know, this is not always possible, or actually rarely possible. Because in practice, manufacturers often receive incomplete or simplified design models at the bidding phase, IFC files, and still need to determine if the project is manufacturable or how it should be produced. So we address this gap through a digital workflow for the reconstruction, rationalization, and planning of freeform Glulam beams. We start with different types of received design input, reconstruct an idealized beam geometry. We calculate the Glulam blank geometry, which is the manufacturing geometry that is actually produced, and we finally generate the material specifications and other information needed for fabrication. So the objective is to create a continuous data flow from architectural model to the factory floor. And here the key challenge comes from the manufacturing process itself. So unlike single curved glulams, which are well understood, double curved glulam is typically produced through two sequential bending operations. So first you make a single curved shape, then you slice it and you bend it out a plane. And during the lamination of the individual lamellas slip and slide relative to each other, and this causes the cross-section to become skewed in kind of complex and variable ways, depending on the geometry. So that means that the geometry that we manufacture, which is the Glulam blank model, is not identical to the final geometry of the target, the beam model. And this relationship has traditionally relied heavily on tacit experience, internal knowledge, manual interpretation, and very craft-based methods. And this problem is also compounded because design information is rarely ideal, as I mentioned before. Manufacturers are often involved only after the design is largely complete, and the available geometry may consist only of coarse solids, simplified representations, meshes, or sometimes overly detailed elements. So just a couple examples from projects in the images there. So a detailed NURBS model and a coarse mesh extracted from an IFC model. So our workflow therefore begins by reconstructing a usable geometric model from whatever information is available. The first stage is geometric reconstruction. We use a heuristic to identify the most likely beam edges and generate an approximate sweep, a kind of idealized rectangular sweep with a constant cross-section that becomes the kind of ideal beam geometry that encompasses the design target. The beam surfaces are then unrolled into flat space, or otherwise the kind of local curved space of this idealized beam. And then from there we calculate how much skew develops during manufacturing and what are the extents, how much do we need to expand the input material by to make a good blank. So from this information we generate the actual Glulam blank, the geometry that must be pressed, so that after deformation it encompasses fully the target beam geometry. And then finally this blank model is used directly to position and orient the press. Now the same model also provides material specifications because from this then we can pull out all the necessary data we need to make sure we're within material limits. Maximum curvatures in the Glulam blank model are analyzed and related to allowable strain limits that are derived from Eurocode requirements. And then this determines appropriate lamella dimensions. We've also done some preliminary studies using 3D FEA of the bending process to identify strain values through simulation. That's quite early at this stage. And then at the same time, we have a parallel study that's following the material properties of individual lamellas throughout the production chain. So at each process step, to understand how each process step affects key performance indicating properties of the input material. And the kind of merging of the two, it suggests that future versions of the workflow can also better connect geometry with these changing material properties throughout the production process. So to validate the workflow, we produced 15 reduced scale freeform Glulam beams using 15 by 50 millimeter lamellas. And then we used LiDAR scans of the finished prototypes to compare against the digital models. So just a side note on the scan at the bottom, the red points, the blanks are longer than the model, which is why the ends are far away from the model because they're longer. So across the specimens, we achieved a mean geometric deviation ranging from roughly 0.3 of a millimeter to just under 4 millimeters, demonstrating that the automatically generated production parameters produce geometrically accurate beams. And then if we look a little bit closer to this, 9 of the 15 prototypes had over 90% of the measured points within 10 millimeters of the digital model, while 4 prototypes had over 70% of their points within 5 millimeters. And we also observed that due to the pressing sequence of the production process, the second pressing stage consistently produced larger deviations, so suggesting spring-back effects in the thicker lamellas, which then would need to be accounted for in future simulations. And from the prototyping and validation, we also see that integrated quality control emerges as an important next step in the digital pipeline, probably through some sort of integrated scanning or other kind of detection system that we can also connect to the digital workflow. Alongside the digital workflow, the production equipment is being developed in parallel. So the press itself is an array of articulated jaws that are independently constructed, and this has implications for the digital model because that means that the kinematic model can be separated and thus solved directly, so we don't need any kind of complicated kinematic model of an entire press chain. And so the same Glulam blank model generated by the workflow directly defines the position and orientation of each pressing head, again, tightly linking digital design with machine control. Our next step is to connect the limits of the press more closely with the range of possible forms, and to also look at how the press itself can be motorized to kind of make this data flow even more seamless. So to conclude, we ultimately envision a fully automated industrialized process for fabricating freeform Glulam beams from coarse input data. We've demonstrated a digital workflow that transforms variable architectural input into manufacturable freeform Glulam production data. The prototype study shows that the generated parameters are sufficiently accurate for fabrication, while also identifying where improvements are needed. And then looking ahead, we see opportunities to integrate quality control feedback, improve the relationship between material behavior and process planning, and eventually incorporate other methods such as statistical analysis, machine learning, etc., to rapidly estimate production parameters from previous projects. So we would be happy to chat and answer any questions. Thank you very much.